Hello all, this is VLSI update. Hope you all are doing well. In this session, we're just going to cover on basic digital design and how to start from the block diagram. And this is going to be like a hands-on session, and we can have a block diagram and how to get started from the block diagram and with the input and output ports definitions, and from that, what kind of functionality you want to implement. Okay, it is important for not only for the smaller designs, even for the bigger designs. It's actually good to start from the block diagram, and the block diagram doesn't have to explain what kind of low level circuits are going to be like. Is it going to be a counter? What kind of flops or what kind of resources is going to consume? Doesn't have to be at all. Just draw a block diagram, have the input and output ports, and that input and output port you can start defining in the before you start writing the hardware description language. Okay, so just wanted to have that session quickly. Here just wanted to cover about the counter. We have variety of counters like asynchronous, synchronous, up, down, and bidirectional, and Johnson's counter, and all. So among these counters, synchronous counters are mostly used because of its the clock is being used commonly across all the flops, and it will increase the speed and the reliability, and also due to that features, we are going to go for the synchronous counter. And what type of flops is being used for the synchronous counter, right? So as I said, like the clock signal is common to all the flop. The speed is much better than the asynchronous counter, such as ripple counter and all, right? So here we don't see any issues like skews or glitches and all here, and it's reliable and faster, and it primarily uses the D flops or JK flops, but in most cases you see the D flops in any designs. If you take for ASIC and FPGA, it's common, and it can be like the reset is easy for a synchronous operation and all. Okay, so let's see how to get started with this design, and we're going to have a hands-on session also where we start writing the Verilog program and all. Yeah, this is the block diagram I was telling you. So in this block diagram, if you take, we have the clock input and the reset input, which are basic input to any block. Apart from that, there is the data input. In this case, I'm not going to use the data input. I'm going to assume the internal counter output itself. I'm going to take the feedback of these and start from the 0 to 1 and on. If you have any specific requirements, I want to start from this particular value. In that case, you need to add one more control signal also, like enable or load and all. Okay, so the whatever the control signal you add, it will add more logic in that resource, in that particular resources. Okay, so if you take in this logic, I have the clock and reset. If you want to add more load and enable and all, it depends on the operations. Okay, it will create additional logics. That's additional logics in the resources. Okay, if you're adding some synchronous reset, it will add some additional mux over there. We're using some asynchronous reset. It will be a little bit difficult for the timings and all. Okay, so that we need to keep in mind. So in this block diagram, we have the clock, reset, and the counter output. So with this, we can start our basic Verilog coding and see what kind of resources is getting, inferred. And I'm going to use Vivardo for these things. Let me go to Vivardo. Basically, I'm good in hands-on here, so let us jump into the hands-on part. More than the theoretical part. So, let me very long time. Let me put on count n bits. Later we can change this. The file is just getting updated, and yeah, count n bit here. Okay, so it will have a time scale and module and end module. So with the count n bit name. Okay, here I'm going to define my input and output ports. As already mentioned in the block diagram, my input ports are clock and reset, and my output port is count output. Okay, so I'm going to define the number of bit width of the output counter. Now I'm going to assume for 4 bits, so it's a 3:0 and count output. in Verilog model, we need to define the type of the signal, whether it's a register or wire in the output area. For the wire, it will assume implicitly, but if it is going to be registered, you need to mention explicitly. Okay, I'm going to assume this as a register. I'm going to use this in the always block itself. Okay. So now, this is my input and output ports declarations. Let me mention that. Port declaration. So clock, you can assume any frequency. Okay, frequency you can assume. Let's select 10 megahertz this operation. And for the reset, I'm going to assume the synchronous reset for this operation. Okay, so you can go for asynchronous reset order. It depends on the design requirement. And we have the counter output. This is the my counter output here. It is always good to write commands for the each line in the code for the better readability here. Now let us move into the always block. So always block, which will have a sensitivity list. Since this is the sequential block, the clock is must in the sensitivity list. Okay. So passage of clock, it can be passage or neckage, and the synchronous reset I'm not adding here because it's synchronous reset, so we don't need to mention it in this block. Okay. So only the sensitivity list. Since it is sequential block, the clock is must here, and begin and end. Let me start with the reset. Okay, so this is again synchronous reset. So why do we need reset signal in the ground? I'm putting begin and end. It's not required if you're using only one statement, but yeah, I'm just giving it for the reference here. So I'm just going to assume my count output initially at 0. So this is to initialize the register. Why do we need these registers here? To initialize the register. Okay. So this is very important because even in hardware, like the hardware doesn't know from where to begin, right? So if we do not initialize to some known value, it will assume some unknown values like x and all. Okay, and if you cannot add something to x, if you add something to x, it will give you the x only, right? So it is better to better to initialize register values. So the reason to do that job in simulation, use some initial block runner, but in hardware we do not have any option like that. Okay, so we need to use reset for the registers and initialize those values. Okay, in order to start from the known values in that case. Okay, so to initialize the registers, and I'm setting to 0 value, initialize to 0 here. So after that, else condition, and else condition we can have that counting operation. So here count out plus 1. This is my increment operation here. So every time it will increment to one value. So increment operation from 0 to 15, since it's a 4-bit value, it will increment till 15 and then it will come back to 0 again 15. It will cycle like that. Okay, so yeah. So this is my basic counter code, synchronous counter code. Now let's see what kind of the schematic and the resources it gets inferred in FPGA. Okay, let me get that RTL schematic here. Okay, so we need to set this as a top level module. Let me yeah, just taking updating the. I just need to update this to the top module, and then I have to do the schematic for the same. Yeah, it's let me update this to the top module, and count 10 bits. Let me open the schematic for the same. This is the RTL schematic, which will tell what are the resources are getting inferred based on your RTL design. Okay, but this is not the actual resources of FPGA or something. This will just explains. If you design some mux kind of, it will show the mux symbol. It will, if you design some flops, it will show the flop symbol. So if you did some additional operation, it will show some arithmetic operator over there. Okay. So yeah, so this is our synchronous counter operation. In this case, you can see two resource inferences. One is the arithmetic operator, another one is the registers here. Okay, so this will be used for the increment operation, and this is our actual registers. We have, if you see, this is the overlapping. Okay, so we have the 4-bit register here. So since we designed the 4-bit counter, so the output of this will be fed back to the uh, these arithmetic operators. So every clock cycle, there will be one increment. Since we set it to the one increment, so it will take totally the 15 clock cycle to finish 0 to 15. And like if you want this to happen faster, like for 7 clock cycle, you need to update this increment value to 2. Okay, so see here, if you see, it's updated to 1. Here we are not providing any external input here. We just assigned the initial value as 0, and we are feeding back the output. So this will store the values, the previous values, and that will get updated in the next clock cycle. Okay, for every clock cycle there will be one increment here. So this is a basic operation here, and this schematic will tells us like what are the it's not the low level resources. What are the high level resources are getting inferred. Okay, if you see, this is not the actual resource here, right? In FPGA, like and an ASIC, this will get inferred. This will get implemented using some some arithmetic block. Okay, kind of thing here. So this will show the symbol of that. If you symbol of like what kind of symbol are getting inferred, and for easy understanding here. Okay. Now let's see like what are the resources are getting consumed in FPGA. So for that we need to do synthesize. Let me initiate a synthesize on these. It will take 1 or 2 minutes and we can get the results immediately. If you see here, like yeah, the ports we are using is like data input and the clock and the reset and the queue. This is synchronous reset here, and the counter output here, and we have the constant one here, and the feedback is getting fed to the arithmetic operator here. Let's wait for the synthesized results so that we can see what are the resources are getting consumed. Okay. So in FPGA, like we can see the resources wise, LUTs, flops, and VRAM, URAM, DSP, IO, GT, PUFG, MMC, MPLL, and PC, and all. So in this case, like for the arithmetic operation, it's a very low bit arithmetic operation. So it's like it can use LUT itself. Okay, and for the registers, it has to use flops. We can see the 4 registers are getting used, so it has to be 4 flop. And for the arithmetic operation, it should use 1 or 2 LUTs here. And VRAM is something like a dedicated memory resources in FPGA, and URAM also is a dedicated memory resource, and we are not going to use this. So and then DSP slice for the complex, arithmetic operation, and this is not going to be used here. And the IO count, as I said, IO count, what are the inputs you're providing, what are the outputs you're getting. This is really important. In a smaller design, we don't see the number of IOs and all, but in a bigger designs, we might end up in having limitation to use all the IOs. So we must be very careful when we are going for the bigger designs and all. And GT is for the high speed transceivers. We are not going to use this. And BUFG will get inserted by the tool itself in the clock path. MMCM is for the clock operations like multiplication, division, and all. So here we are not going to use them also. So, and the PLL, there is no PLL, there is no PC. As I said, this is completed now. You can see here. If you see the resource consumption here, LUT is 2. LUT is for the arithmetic operation here. Okay, and the flops are 4. 4 bit flop. If you're using the 6-bit counter or 8-bit counter, this flop value will increase according to that. And apart from that, we have there is no BRAM, there is no URAM, there is no DSP slice, and there is IO count of 6. Reset and clock and the 4-bit output here. So this is a 6 IO counts, and there is one buffer C, and there are no other resources are being used in this FPGA platform. Okay, so now this is I just designed for only 4-bit counter. You can make it as a generic using the parameter options in Verilog. If you go to the parameter option, you can just define one parameter mention the count with. When I say n-bit counter, you can define any count with whenever you can change this count with whenever you require, right? So if you mention that parameter here, so the value changes you make in the top field, it will be get impact. It will get reflected here as well. Okay, so this will be useful when you have a bigger designs on all. You'll design your you'll put your counter somewhere part of the design, and if you want to make a change, you cannot go and find out that particular register. If you have 17 registers also, in that case you need to make a change there as well. So there's a little problem for that. So if you define parameter in the top level itself, you just change the value here. It will automatically get updated through this the count width. Okay, so like that you can change the count width based on your requirement. You can design 16-bit, 32-bit, and see how much registers are getting used, how much LUTs are being used, and if you go for high number of arithmetic operation and all, like 32-bit and all. So what happens? It might start using the DSP slice by default. There will be some threshold kind of thing. If you exceed that number, it will automatically start using DSP slice and all that. And all you can experiment and see. Since this is a basic counter, we are not seeing that DSP slice and all. If you increase this count width and all, you will start seeing all these details and all. Hope this is helpful. I just wanted to have a quick discussion on this, and just start practicing on this. Take any basic design, since Vivada is free license only. You can start writing any basic code and start seeing the schematic and and the resources consumption. You can even go for simulation also. Start writing your own dispatches here, and we have the simulation option. If you go to sources, we can add your simulation sources here and start creating your own test benches, pass the clock, and reset and all. From the test bench point of view, you can see the simulation point of view also. Okay, hope this is helpful. Keep practicing. I will be pasting this code in the YouTube link or the LinkedIn link, and just keep practicing. Like have the command session and all. Okay, which will be easy for the readability of the code and all. So keep these things in mind while doing your design, and yeah, this will be really helpful. And let's catch up in another session. Okay, thank you all. Bye.